So, good morning, everybody. Um, I know it's quite early, so I want to speak about adaptive loudspeaker control based on LAMP parameter modeling. Those who've been to Mr. Klippel's presentation yesterday, they might be familiar with some of the things I will tell you, but maybe also for those there will be some more information and go more into detail into the control system of the loudspeaker. So, at first, I would like to say a few words about why we would like to do some adaptive control of loudspeakers, and then we come to the objectives. What shall a loudspeaker control system should do with the loudspeaker? Where should it help? I would like to present you our implementation of such a system and come to the challenges and our solutions to the problems you issue if you drive a loudspeaker really to its limits. Finally, some conclusions. Here you see the operational range of a loudspeaker over amplitude, meaning displacement amplitude. And usually if you apply little amplitude to the loudspeaker, you can describe it with a linear model. You're quite fine with all linear techniques you can use. But you see there is a lot of possibilities. There is a large region, we call it the large signal performance region, where you could use a loudspeaker. In fact, it would work there, but it suffers from certain issues. So if you want to use a loudspeaker there, or if you would like to model it at first, you would need to consider nonlinear and thermal parameters, nonlinear and thermal effects, and they are closely related to the maximal output of the loudspeaker. So if you want to get to the maximal output of a loudspeaker, you will encounter distortion generated by the speaker. You will see some compression, thermal compression, mechanical compression, and maybe even the loudspeaker may get unstable at higher amplitudes. And you see, you get very close to a region, we call it overload, where the loudspeaker may be damaged and you have to do something against. So how can a DSP or signal processing, in fact, can be used to operate the loudspeaker over the complete available operation range? Of course, at small signal performance, we can apply some equalization. But if we get to large signal performance and we would like to have equal sound quality or acceptable sound quality, we would come to that we would like to have some linearization of the loudspeaker. And like that, we could exploit the usable working range and get more out of the physical resources of the speaker. If you get really to the limits, you might need some methods or some means for stabilizing the loudspeaker. And certainly there will be some hard limit where you shouldn't drive the loudspeaker beyond, unless it gets, otherwise it will get damaged, it will be destroyed, and you need a protection system, an electric and a secure protection system for avoiding the loudspeaker getting damaged. So from that, we can derive some objectives for loudspeaker controls, assuming we have some digital controller taking the audio input and providing it to the loudspeaker, and before we can implement whatever we like to fulfill those objectives. Of course, we are first interested in more acoustical output, meaning we would like to get the most passband sound pressure, and of course you would like to have as much bass as possible, considering the constraints, the physical constraints. And we would like to have that sound output at acceptable quality, meaning we don't like to have too much distortion, signal distortion, regular distortion, and of course also not irregular distortion like rub and bass. Another objective would be to to reduce the power consumption of the loudspeaker if possible. And you would like to have all those with smaller sizes, smaller enclosures, considering all the constraints for marketing and consumers. And we would like to have it at lowest cost possible. As I said before, we need a secure overload protection. We need to detect the thermal and mechanical limits of the loudspeaker and don't drive it beyond. And we would like to assure some long-term stability and coping with climate changes, aging of the speaker, especially the suspension is very susceptible to changing parameters. So our loudspeaker modeling is based on a nonlinear lamp parameter model. So you're probably familiar with some equivalent circuit of the loudspeaker. We have linear terms, and we also consider nonlinear lumped parameters like the inductance related over X and also I, and the BR, the force factor related over X, and stiffness over X. For frequencies below the cone breakup, this lump parameter model can exactly describe the performance of a loudspeaker. And having such a model of the loudspeaker, we can use that for applying some adaptive loudspeaker control. Here's a graph for the control. So we take some input signal we want to reproduce, some audio input signal set, process it, and then play it via an amplifier to our loudspeaker system. The control is based on the transducer model and the parameters, and it's a feed-forward structure. That is very important. We would not like to have any feedback in the audio processing because it might get unstable, and we cannot control it that well. And a good property of this structure is also we could switch off, or we could operate the processing with frozen parameters. That means we don't need to update the parameters all the time. Here you see the second system which would be required for getting the parameters. We do this by measuring state variables, and the best idea to measure the state of the loudspeaker is actually using the loudspeaker itself as sensor. So we are measuring voltage and current from the speaker terminals at the speaker terminals, and from that we can learn all parameters of the loudspeaker. We need this learning for being adaptive to climate changes, to environment changes. I will show that later. And those parameters, they can be fed back to the online processing, but it's a parameter feedback. That means it's not time critical. We can introduce delays, and you should have it active from time to time to get new parameters, but there is no signal feedback which could introduce any instability. The parameters can be stored in a memory and used for startup. They can be analyzed, they have a physical meaning, and all this system can be implemented with quite low processing load, meaning currently it can be implemented on a microcontroller for woofer systems. Okay, I'd like to go a bit more in detail at first in the parameter identification system. How do we do that in detail? We measure only electrical systems at the loudspeaker terminals. We don't need the audio input, in fact. We just measure what is the voltage and what is the current. And now we would like to adjust our model of the loudspeaker to the real loudspeaker. So we have our model, and we would like to estimate the parameters of the model. And that can be done by minimizing the... Just 1 second. Maybe I come here. It can be done by minimizing the error between the model signal and the real measured signal. So we have some parameter estimator which uses the error signal and the state variables produced by the model to update the parameters until they are optimal for the given signal. So it's this very simple updating mechanisms based on these mean square algorithms, and we need good conditioning of the electrical signals for learning all parameters. So we need a good excitation signal. Currently, we do this with an initial identification to get proper parameters of a loudspeaker with some noise signal, and later on you can live with any music signal, but you might need to reduce the parameters which are updated. So if the signal is poor, for instance, it's just a pure sinus signal, we cannot update all parameters of the loudspeaker. We need to check for a persistent excitation and maybe just only update one parameter like the voice call offset and don't try to identify nonlinear curve shapes at the same time. Yes. And the identification is decoupled from the online processing. It could even be at a different in a different hardware unit or whatever. It can live with noisy signals, it can live with downsampled signals. It doesn't need to be audio quality in the parameter identification. It's the opposite for the audio signal processing. Here we have different constraints. We again use the transducer model, same transducer model. And from the parameters we obtain by parameter identification, we can estimate now what is going on in the loudspeaker. We know the displacement of the loudspeaker, the temperature, the current. Those we call states of the loudspeaker. And those are required for an adequate protection system and for linearization of the loudspeaker. At the same time, if we know the instantaneous parameters, we can apply some fixed system equalization, system alignment. So we would like to linearize the loudspeaker, reduce the distortion generated in the speaker. We need the protection system to protect against thermal mechanical overload, and here's a system alignment. And all that we would like to have was a zero latency, so there's no additional latency introduced in the pure audio chain. This kind of control structure is very robust, is feed-forward all the time. Even if the parameters are not perfectly fitting to the real loudspeaker, we cannot, we just produce maybe a bit more nonlinear or linear distortion, but we cannot make the loudspeaker unstable or producing any feedback loops or things like that. And the audio processing is also implementable with low processing load as well. Here's a short look how we think an automatic system alignment can look like. So we start with our audio input, and we would like to have a certain transfer function between the audio input and the produced sound pressure by the loudspeaker. For instance, we'd like to have a 50 hertz cutoff frequency and some Q factor, and to assure that total transfer function looks always the same. And we would like to, we start with identifying the real transducer, and given that we have applied linearization and stabilization, the transfer function from the input here to the sound pressure is a linear one. Otherwise it would be nonlinear and not stable. But as we use those, we can identify that linear transfer function. This is changing. It's changing with temperature, it's changing with load. And we identify the current parameters, and from given target values by the user, we can apply a automatic alignment to the input here. So the alignment and the linear transfer function of the loudspeaker together give the total transfer. We can even provide some diagnostic information for system optimization. Okay. And here's a picture you have seen yesterday, maybe. The resonance frequency of a driver is not constant, you already might know, but it's really dramatic changes, changing with temperature, with humidity. Here, for instance, there are plotted two different woofers, automotive woofers, from -30 to 80 degrees Celsius. And you see the resonance frequency might change by 2 octaves, factor 4 in resonance frequency, meaning factor 16 in stiffness. That's a lot. Even from ambient 20 to 40 degree, it's a huge difference. You cannot apply the same alignment function and assume that your total system looks the same. Here are some simulations from an alignment of a banded box, and you see, depending on the current temperature, you get totally different behavior of your loudspeaker. But if you know the parameters, the current resonance frequency, you can keep your desired alignment, or you can even give some mercy to the loudspeaker. If it's too cold, you don't keep it, but you make some softer curve than those two resonances here. So in fact, we need some adaptive learning processes, but as you see, the temperature here is not changing that quickly, not that dramatically, so we can relax with the adaptive process, maybe switch it off for some seconds. We are still right with our parameters. For instance, if there is some silence in the music signal, and switch it on again when the excitation is properly. Here's a focus on the protection system. So we would like to assure thermal and mechanical protection of the loudspeaker. We are doing that based on the voice coil temperature and the real displacement of the driver. And if the voice coil temperature gets too high, we need to attenuate the total signal. There is no way around that. And if the displacement is getting too high, we adjust some variable high-pass filter, removing or reducing the bass first to keep the displacement within the mechanical limits. And we use the same parameter identifications, the transducer parameters, to estimate or to predict the displacement and voice coil temperature in the transducer, including any DC which might be generated in the driver. So the control system provides full protection against overload. It can automatically identify the limits of the working range during the identification phases. And it allows the maximum sound pressure output, exploiting all the limits. Of course, it should not generate artifacts in the audio signal and don't introduce more distortion. It should be operatable for any signal, so it doesn't matter what you play with a loudspeaker, you should not be able to damage it again. And if required, it's possible to do that all with zero latency. But you see there is some contradiction. If you have no latency, you might have some artifacts, or it might become audible, but if you allow a few milliseconds, 1-2 milliseconds delay, then we can reduce the artifacts to zero. And what is also interesting, you can get diagnostic information from the protection system. How much is it activated? How is the bass changed? And you can use that for overall system adjustment. If you have multiple speaker systems, you would like to reduce the we would like to attenuate all channels. It's the same way you can do that. Here's an example of the mechanical protection system. That one is that the protection system is with 0 delay, and we played a sinusoidal 25 Hertz tone. It was directly switched on at the maximum of the sine. So this is like a worst case for a protection system. And you see, we would, if we apply this voltage, if we would have applied the voltage to the speaker, we would get 4 times the displacement which was allowed. And you see, we need to identify, or we need to anticipate the peak of the displacement in a very early stage. Because only if we know it in advance how high the displacement will be, we can react in a proper way here to avoid that and to stay beyond the limit. So what we do is some prediction of the peak displacement. We know about the energy in the signal, and we can have a time advantage of a few milliseconds, so we can activate the protection smoothly. Here you see what happens with the input voltage here. The input voltage was switched on immediately. And at first, in the first millisecond, the complete signal was played to the loudspeaker because it was safe, the displacement was safe, the kinetic energy was safe. But then we detected it will become too much soon. So we reduced the low frequency. Here you see the high frequency remains, and the output voltage is very quickly reduced to a quarter, so the displacement will not exceed this maximum. And another issue is if we want to use the complete working range, we don't want the protection system to get activated without need. So here is an example where we are exactly at the limits. And if we are exactly at the limits, we don't like to have any reduction of the output. So at the same time, we want to be very sensitive, to be quick, to react quickly on high peaks, but we would like to be relaxed and not do too much to the signal. Here you see an example of the thermal protection. For instance, if you play a sinus tone with high amplitudes, you're heating your driver very well. And here the sinus tone was switched on. And you see at first the voice coil temperature rises very quickly. Maybe in a few seconds it's getting very hot. But then you start heating your magnet system, the environment a bit, the air, the pole plates. And that has a much longer time constant, can be an hour for a large woofer. And you see then the voice coil temperature rises more and more, and we have to reduce the input power more and more to keep the voice coil temperature beyond the limit, which is acceptable. And you see here also we cannot predict the temperature, or it would be possible, but we don't predict the temperature due to the magnet or due to environment. You cannot predict the environment temperature at all. So what we need is a measurement of the temperature all the time. It can be slow, it can be at a very low, at very low level, at very low time scale, but we need to get some measurement feedback to adjust to heating of the magnet. Now let's look quickly to the linearization of the loudspeaker. Assuming this would be the distortion generated by the speaker itself, we would like to pre-process the audio signal in a way, add some synthesized distortion with opposite phase, equal amplitude, and if it works, then the residual distortion is much less or zero. How do we do that? We are very lucky with the major distortion mechanisms in loudspeaker. They are very close to the input voltage. They are in a one-dimensional path. Here is the motor, basically, of the loudspeaker, and this is the radiation, the cone vibration and radiation to different points in the sound field. And all the nonlinearities, the dominant linearities, are in the motor, in fact, are in the one-dimensional signal domain, so we have good opportunities to reduce the distortion which is generated here. And you see the loudspeaker is a feedback system itself. So we can derive directly a control structure from the transducer model. If we would subtract the distortion, the same distortion as which is added here at this point, then we have linearized the loudspeaker. So we need a similar nonlinear system. And if we have that, you can see that this point here is identical with the input. So we can in fact use the input, the audio input, and generate the distortions, remove them from the audio signal, and later on they will cancel out with the distortions generated in the loudspeaker. And this point is linear, and this point is linear as well. Here you see some mirror symmetry. We're using the parameters from the loudspeaker, apply mirrored electronically before, and we get also interpretable state variables like that. So we have the same displacement in our system here as it is in the real loudspeaker. It is a very nice feature of this control structure. Okay. Here are some graphs what we can reach with that. Considering harmonic distortion, if you compare nonlinear controlled loudspeaker without control, you see the harmonic distortions can be really reduced. Of course, we need accurate parameters for that. We cannot do anything against breakup modes, but we can face the major nonlinearities, BL from X, KMS from X, or inductance from X or I. Yes, and the reduction depends on an adequate modeling. So if our model parameters are not perfect, the reduction will be less exact. Here you see the same for intermodulation distortion. Intermodulation distortion might be really even more unpleasant than harmonic distortion because it's broadband and in the voice range. And here you see also we can reach a good reduction for second or third order intermodulation distortion. You can also see it in the time signals. Here a bass tone of 50 Hz is intermodulated with one kilohertz tone, and if you apply nonlinear control, it's much more stable, and you don't have those intermodulations as you see here. But there are some restrictions on this control. As I said before, we need to know the right parameters. So we need to know what's going on in the loudspeaker. And we can only learn that from voltage and current. So if there is no current flow in the loudspeaker, we don't know anything. And at the same time, we need some persistent excitation. If you play only a single tone, we cannot identify, we don't have persistent excitation, and we cannot identify our parameters. We don't have the information in the signals we measure. So we need to disable the parameter identification, because otherwise the parameters will become biased, they will become wrong. They are not what happens in the loudspeaker, but They explain very well the distortions generated from that sign, but they are not the true loudspeaker parameters. And if we disable the parameter identification, so we cannot assure perfect stabilization of the transducer. Our linearization gets worse, our protection system might be not perfectly adjusted, and also the stabilization is not working well. So we need to do something, and our idea was, or is, just one slide in between. Here you see how accurate we need to be for reducing the distortion. So we need to have a very low error in magnitude of the distortions. If you get to 3 dB error in magnitude, you end up with 10 dB distortion reduction, and we need to be very exact in phase, maybe 10 degree, 15 degree, and then the distortion reduction gets worse, and you might even introduce more distortions than had been without control. So our idea is now, if we don't learn all parameters, we might be able to learn just one parameter, and that might be sufficient to explain the instantaneous changes in the loudspeaker to a certain degree. So we don't learn a different curve shape of the BL curve, but we shift all curves, all linear curves, to the right, to the left, to find the perfect position where currently the voice coil is located. We can do that because the parameters P, in the vector P, they are slowly time varying. We can learn them with a slow learning constant, but we need a persistent excitation. On the other hand, the voice coil offset, it might be changed very quickly. Depending, for instance, if you have a sealed enclosure, it might be less quick because it needs some time to generate DC in the loudspeaker. The stiffness of the air holds the loudspeaker at this position. But we need some high learning speed, and we need to update it all the time. We don't store it in memory because there is no real meaning for that. We just start from zero when we're powering up the system and try to identify it as fast as possible where the loudspeaker is really. Here you see a practical evaluation if we play some sinusoidal stimulus. Here there were some sinusoidal signals, and they were at the resonance frequency. So if you assume an asymmetric force factor curve like that, and you play a signal at resonance frequency, there is no DC generated from this force factor nonlinearity. That is because BL from X will be multiplied by I, and they are 90 degrees out of phase, so there is no DC component generated. And the voice coil offset remains 0. But if you're far below the resonance frequency, there is a tendency in the driver to be self-centering. So if you have a maximal force factor which is asymmetric, which is maybe here at 1 millimeter, then you will see that the loudspeaker has a tendency to move outwards to this maximum. And you see in the signal during the sinus, the loudspeaker went a bit out, the DC moved out, then it recovered, and we have learned that during that time as well. If you look at the impact on distortion compensation, we have to distinguish even order and odd order distortions. So here you see harmonic distortion, third order harmonic distortion. And if we compare here you have no compensation applied. The red curve is control on, and X offset was updated. and the green curve, there were no updating at all. And you see, we are not much worse, maybe at very low frequencies, but we are very equal in performance, even if you don't update the voice coil offset position. But it looks very different if you look at second order harmonic distortions. Here you see below resonance frequency, I think the resonance frequency is somewhere here. Below resonance frequency, if we don't update, we might even be worse than the true loudspeaker. So we generate more distortions than the true loudspeaker because we are not at the right position with the voice coil offset, and that is it's mainly producing second order distortions if we have a voice coil shift. But if we update the voice coil offset as one parameter, we are very fine again with the distortion reduction. Now just a short outline of next steps which can be applied. So if we have an AC coupled amplifier here, we cannot do anything against the voice coil offset. All what we can do is considering it in our audio processing to generate the right distortions and to adjust the protection system properly. But what we would like to do, so if we had a voice coil offset, it would be very interesting to compensate actively that offset. We would like to shift with a small voltage, DC voltage, we would like to shift the voice coil at the optimal position where we can exploit the most working range of the loudspeaker, where we have highest efficiency. But for that, we would need some DC injection in the amplifier, at best some DC coupled. Some DC coupled amplifier, and at best with a digital input. If you have an analog input, it's a very dangerous thing to add some DC. But if you have a digital input amplifier, you can add the desired DC voltage and it will shift the rest position of the driver to the optimal position. For that, we would need some offset compensation, add a small DC voltage, a few hundred millivolts or even less might be sufficient to have it at the perfect position, the loudspeaker. So let's summarize what I presented here. If you want to have a small, a light and efficient transducer, you cannot avoid the nonlinear behavior, but those nonlinearities can be modeled very well with lump parameters, and based on that modeling, an adaptive control system can cope with those nonlinearities and ensure optimal position, optimal performance of the controller for any input signal. We need to identify the speaker parameters, at least the temperature and the voice coil offset. And if we would have a DC coupled amplifier, we could even shift the voice coil to the optimal position. So finally, there will be new degrees of freedom for speaker design in presence of an active control system. I think you will hear in the next presentation from Mr. Klippe more about that topic. Thank you very much. No? Well, Mr. Klippe shakes his head.
Yesterday I spoke about that. In the next slide I was speaking about the standard activity to measure output base.
Oh, sorry, so I mixed that. But do you have any questions about that here? Please.
If there are any questions, I have the microphone here. Questions?
When you showed the distortion reduction, you showed a reversed polarity version of the distortion. But doesn't that assume that the system is linear? on the other side where it's not. It's actually nonlinear. So there's going to be that correction voltage will be distorted again by the loudspeaker. So isn't there some kind of loop there between the correction signal and the output?
You mean if the
Yeah, it's in the first few slides there. You showed a distortion.
yes.
And then you showed we're going to do this to it. We're going to use.
Yeah, that's it's just an illustration what we would like to do. Of course, there is some feedback in the loudspeaker. If we are not accurate with our generated distortion, the loudspeaker will produce something else. If we are not accurate with the displacement and the states, then we cannot generate the right distortion. I'm not sure if I answer your question correctly.
I was just curious. The correction signal can't be exactly the opposite of the distortion. That
It's
the
not. It's not the opposite.
Yeah.
That's not true. It's a mirrored signal. Here, maybe I can explain here a bit. The loudspeaker. This is a loudspeaker. It gets some input signal and generates the distortion in a feedback loop like that. So if you add the distortion, this distortion signal is a feedback signal. You cannot derive it directly from here. You have to do the feedback all the time and then converge a long time until you get the real signal here. But in this feed-forward structure, it's very simple. You need just a nonlinear feed-forward system, a nonlinear filter, and you get the same distortion signal here. And if they are identical, they really cancel out each other perfectly. So if you look at the signal, here is a undistorted input, and we add a lot of distortion here. It can be really in order of magnitude of the fundamental. And the voltage is distorted very much, the current is distorted, but if you apply that voltage to the loudspeaker, it will itself generate addition or the distortion, the opposite distortion, and suddenly the displacement and the sound pressure, they are not distorted anymore. They are free from distortion. Okay.
Question?
All this methodology is applied only to woofers, or you may apply it to wideband, let's say small speaker for headphones. Or
well,
whatever.
It's very interesting to apply that structure to any electrodynamic loudspeaker. Of course, it's very interesting for full band speakers because they suffer much more from intermodulation distortions. And it's very interesting for headphones, for micro speakers as well.
If you look at, let's say, distortion as a function of frequency, it doesn't matter if it's harmonics or it's a reaction to multitone. Up to a certain point in frequency, basically distortion go down because displacement, which is the dominating factor, goes down. Can you go to the frequency range where distortion is dominated by diaphragm breakups? I don't think so.
Well, this is an interesting research topic, in fact. We are working on at least dealing with the first cone breakup mode. So when the surround starts breaking up, you introduce a lot of distortion again. It's a mechanical distortion on the cone, but it's a very complicated topic, and we're currently working on that. But I think there is some hope that we can deal with that as well.
Regarding the offset, the DC voltage you apply, is that constantly present once it's calculated, or only when there's DC or active?
Well, I think it will be only necessary when signal is available, when audio signal is available. Actually, this is yeah. I mean, it's we have not finished working on that DC addition, DC voltage. In fact, we're still waiting for the perfect amplifier. Yes.
So the voltage and the current that you're measuring from the loudspeaker, these are going to be transformed through a model that is predicting the location
we cannot measure the displacement of the voice coil. What we can measure is voltage and current and the fundamental and distortions in those signals. And what we do is we have our loudspeaker model. For instance, we measure the voltage and we apply the voltage to our model and predict what would be the current, of what would our model suck for current. And then we compare that to the real current we measure. And that information is sufficient for adjusting the parameters of the model. And if we say our model has only one free parameter, which is the offset of the voice coil position, we are able to minimize the error signal by finding the optimal voice coil position of that.
To explain it in another way, we cannot directly measure any DC signal. It has no value. But the second order distortion, as intermodulation distortion, as harmonic distortion, they are closely related to the DC. Because if you have an asymmetry, you get second order and DC. That means from the second order distortion, we get the parameter information which are related with the DC.
So how tolerant is the model of standard building tolerance? It's a voice coil set like gap. Is there, have you studied that?
Yeah, that is more or less the example what Joachim has shown with frozen parameters. We have no problems usually with third order compensation, third order harmonic intermodulation compensation, but not with second order. Yeah. And maybe if the second order distortion are already low in your driver, forget it. If this is very asymmetrical and we have dramatic problems with instability with DC generation, we are only more if we don't apply a permanent measurement of the DC.
Yeah.
What about a compound driver system like, say, a dual sum? What would you do with that?
Well, when the drivers are very similar, if you have maybe two drivers in series, two woofers, something like that, or in parallel, then we could model them as one system. But usually we will get some problems with that. So the best application is having one implementation of the software for each driver you want to control.
And the other one is if you have a full range system, is your crossover network impedance going to cause the measurement system problems?
Currently, we don't consider the crossover if it's not impairing the frequency range or where the displacement is high of the loudspeaker. You shouldn't have too much problems. It shouldn't introduce too much phase error in this range. So
You're operating below the phase offset of the network. Is what you're saying?
yes. So in fact, it's possible to work on an analog crossover, but the tendency is anyway to go to digital crossovers, and then it's not an issue anymore.
If you have a large DC voice coil offset and you have to compensate with a large DC offset, doesn't that introduce extra heat into the system?
Well, you don't need too much voltage to move the driver. You can use a very low voltage to move it. And at the same time, if you move it to the optimal position, you have much more efficiency there. So if you play music, you don't need so much voltage for reproducing or getting the same sound pressure. So in total, you will need less power than without control.
Okay, let's make this our final question so we can get ready for our next paper.
I think the system is very interesting. How will behave if you are predicting the behavior of the transducer relying on BL and linearities. That's the first point that you pointed out. How it will behave if you had a BL shape that does not reflects what you showed. I mean, a Gaussian shape, but a saddle shape.
So in fact, if we consider voice coil offset just from the BL shape, we need some variation of the curve shape, of course. So if you have a very flat BL curve, we have no information where we are. We cannot know. Maybe we can know some things from the stiffness then. We have all as well, but without some variation, some nonlinear variation of the driver, we have a hard job for finding the real position of the loudspeaker.
No, I meant if you had a BL shape that has a electrodynamic restoring force, so you will not have to take care too much about how is the displacement offset of the voice coil, but just correct the unlinearities of the BL shape.
I'm not sure I understand the question. Maybe we can discuss it later.
Sorry?
We should discuss this later. It's more complicated, I think.
Okay.
So yeah,
No, because the system is very powerful, but you will solve half of the problem probably to detect the DC offset, because the system will try to get to the center by itself.
it depends on the signal. Only at very low frequencies it will do that. We can discuss it later. We are at the exhibition.
Okay.
And
Thank
if you like, we can also demonstrate the system there, and you can play a bit around with or listen to some music or as you like.
Okay. Well, thank you, Joachim. Thank you, everybody, for your interesting questions.